So, to start off, does anybody have any questions about anything? Really? No questions? Like, where do we go when we die? Or like, does the universe last forever? Okay, interesting. Well, the point is, I can't answer those questions, but I can answer discrete math questions, which hopefully you'll have a lot, because the more you know, the more questions you have, because just knowledge leads to more interesting questions and things like that. It's a constant circle. That's how math works. And today, we're going to continue learning section 2.3. We're actually going to finally do our first real interesting argument today. And I hope you guys understand, I hope you guys have some understanding of actually how interesting it is, in the sense that just 3 weeks ago, we talked about arguments as things, right? Things that connect statements, but we didn't really have any proof that they work. There's a lot of ambiguity. And now we're here and we're doing arguments, and at no point did anything seem that complicated, I don't think. I think we're just doing truth tables and it seemed like we were pushing paper, right? But pushing paper, bureaucracy has led us to some amazing results. So let's get started today. And I was going to write down what I just said, because it's important. And that is that arguments connect the truth of premises to the truth of, there we go, truth of conclusions. That's just what they do. That's how they roll. That's kind of by definition, right? So, for example, one argument form that we have goes like this, where you have P implies Q and P, and those are your premises. By the way, I don't know if I made this abundantly clear last time, but let's make it abundantly clear now. Whenever you're doing an argument and you say like P implies Q or P, it's assumed what you're saying is that like P implies Q is true and P is true, right? Just like, for example, if I were to tell you like, hey, the movie Tenet is out in theaters, you're not going like, oh, we got a question. Interesting. The point is you're not going like, or if I were to tell you like, hey, I have a fish, right? You're not going to say like, oh, wait, are you saying I have a fish is true or I have a fish is false, right? If you just say a statement in the real world, it's assumed it's true. Same thing here. So saying P implies Q, or we're saying P implies Q is true, and saying P, we're saying that P is true. And these are our premises. And then we proved last time, we proved that therefore this logically implies our conclusion, which is true, right? And you prove this by showing that no matter what P and Q are, right, if they make the premises true, the conclusion must be true. That's what we did last time. That should be getting us caught up. Anyway, this right here, this argument form is called, or what should we name it? Because we have multiple argument forms. What do you think it should be named? Come on, we got a baby book for everything. Well, if no one has an option, we're going to go with what the mathematicians that first thought of this called it, and they called it modus ponens, obviously, right? Of course, it just looks like a modus ponens. You know, it's a unisex name. The point is, yeah, they call this type of argument modus ponens, but there's more than one type of argument, clearly. Another one is this right here, and that is P implies Q and not P, therefore, I'm sorry, and not Q, therefore not P. So here, these are our premises, and this is our conclusion, right here. So the question is that just static. There we go. And notice that, or these questions for me. And notice that this argument right here is different from modus ponens, right? In modus ponens, you have P implies Q, you assume P, and then you concluded Q. Here you have P implies Q and not P, and you assume, or sorry, not Q, and you assume not P. So this is a different argument, and it's called Modus Cousins. They're kind of cousins. And why do you think this argument is correct? Or valid, I should say, valid. These are argument forms, right? Argument forms can't be correct or incorrect because it requires the premise to be true, but we just have variables here, right? We're not saying these are true or false. We're just saying that if these variables work out, such as the premises are true, then the conclusion is true. But we can't say they're valid. So why do you think this argument form is valid? I have a good feeling about this message in chat. Gotcha positive, question mark. Yeah, because it's gotcha positive, also question mark. You know what? The question mark means you're humble. But let's see some confidence here, right? Yeah, because it's contra positive. Remember, P implies Q is equivalent to not Q implies not P, right? And if you have not Q implies not P, and you know not Q is true, what's that imply? Not P. So here's the proof of that. So if we had, I'll say proof of modus tollens, right? That. So remember, in order to prove that an argument form is valid, which is what we're trying to do here, right? What you do is you say that whenever the premises are satisfied, the conclusion must be satisfied. So let's just assume P and Q are statements such that P implies Q is true and not Q is true. So this is satisfying our premises right here. And so we want to show that whenever this happens, by necessity, not P needs to happen, right? So let's see here. Note the contrapositive law, like you just said, it all comes down to that. Note that not Q implies not P is equivalent to P implies Q by contrapositive law. Which we call it a law, but remember, it's not really a law because it proves it had to happen. It was not made up. It's more like a contrapositive observation. So by contrapositive law, and thus, not Q implies not P.
Oh, sorry.
You fine? Is there a question?
There's no question. I just came in and it turns out I was unmuted while I was talking. Go ahead.
You're good. You're good. You know, you don't need questions to be engaged, have engagement, right? That's what it's all about. So that's not Q implies not P, and that equals true. For example, if you like propose to your girlfriend, right? If you wanted to get, you propose to your girlfriend and she asked a question, that's not the only way to get engaged. I don't know what I'm talking about. I heard the word engagement and I'm rolled with it. But the point is, yeah. So we have that not Q. So since P implies Q is equivalent to not Q implies not P, and P implies Q is true, we know that not Q implies not P is true. There we go. Then, I'll put it down here. Then not Q implies not P and not Q. Therefore, not P by what?
Contrapositive law?
Not really contrapositive law. So let's go through what we've gone through so far. So we've assumed that P and Q are statements that make our premises true right here. And we know if the premise is true, we know if, and one of the premises is P implies Q. If we know that premise is true, then you know that by the contrapositive law, that not Q implies not P is true. You know this conditional is true, right? So we've already done contrapositive law here. That was a key point. Good job pointing that out. But what tells us that if not Q implies not P is true, and not Q is true, we can therefore conclude not P is true? What tells us we can do that?
Modus tollens?
Well, close. Modus tollens is this thing right here we're trying to prove, right?
That's true.
Yeah, yeah. In the chat, we saw modus ponens. Because look at this, right? If we kind of put parentheses around and look at it this way, we're just saying, this argument right here is saying that if one thing implies another thing, and the one thing is true, therefore the other thing is true. That's exactly what modus ponens is. It's a little confusing because we have nots here instead of p's, but really it's like the not q is your p here, and the not p is your q. That's kind of what's going into these, right? And so this idea that if one thing applies to another thing, and another thing is true, and the one thing is true, therefore the other thing is true, that's exactly what modus ponens is saying, right? Modus tollens just flips it around a little bit with the contrapositive. And so this works by modus ponens. So we can say, thus, not P is true, so modus tollens is valid. So are there any questions about that? Really all we did here is say by the contrapositive law, we can we can make this equivalent to not Q implies not P. And then once we have that, well, if we're just saying if something, then another thing, and if something's true, then not P, which is modus ponens. So we're just kind of applying modus ponens to these two things right here. Does that make sense? Maybe? I hope this makes sense. Meditate on this. But, of course, there's another way to prove an argument valid. What's another way to prove an argument valid?
A truth table.
Truth table. That's the answer to everything in this class, right? Everything theoretically comes out of truth tables. So, actually, not everything. We'll see why later. That's where things really start heating up. But anyway, right here, where we could use a truth table. So I'll say alternate proof of, there's a second on there, of modus tollens. Use the truth table. And so if we look at so let's go ahead and fill out this table right here with all the possible options for P and Q. So P and Q, right, they can be true, 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 false, false, true, false, false. We've written that 10,000 times, right? These are possible options for P and Q. And then in the case where you have true, true, not Q is false, opposite of true. And then P implies Q is true. In the case where you have true, false, not Q is the opposite of false, which is true. But P implies Q, I mean, that's going to be false, right? Because P is true, the if P happens, but then Q does not follow, so that's false. In the case where you have false true, not Q is going to be false, opposite of true. And then P implies Q, oh, that's going to be vacuously true, right? So this is true vacuously because the hypothesis is false. And then if you have false, false, not Q is true, and P implies Q, vacuously true again, because the hypothesis is false. So we get this. Now, remember, what we're saying, if modus tollens is valid, what it's saying is that whenever the premises are true, the conclusion must follow. So let's look at all the places where the premises are true. The premises are true only where P implies Q is true and not Q is true, right? So let's see. Here, P implies Q is true, but not Q is not true. So this is not one of the cases where the premises are satisfied. Here, not Q is true, but P implies Q is false. So the premises are not satisfied. Here, not Q is false. So again, the premises aren't satisfied. Only this last place are both the premises P implies Q and not Q satisfied. So this is the only possible case where the premises are satisfied. And then notice, in this case where the premises are satisfied, P is false. So thus, in one case where premises are true, P is false, i.e. not P is true. So if the premises are satisfied, it must be that not P is true. So that means that whenever you have statements that work like this, you know not P must be true. That's how you make your argument. So either way, either proof, whichever one you like better, the point is we could proven that modus tollens is valid. Any questions on that?